As we go through this final video in this series, I would just like to talk a little bit about some ways of coping in this time of isolation that we are experiencing. And that has to do with your management of light. And in your anatomy course, you've probably talked about the IPRGC, the intrinsically photosensitive retinal ganglia cell, and its effect on circadian rhythm. So you want to use that to your advantage, that little cell. During the day, you want to stimulate it because it causes the secretion of melanopsin, which suppresses melatonin. And melatonin is your at-night drug for repair and growth. And during the day, you want to suppress that melatonin and have your body be active. And so you want the IPRGC is responsive to blue light. So during the day, you want to be active. During the night, you don't want to have the effects of blue light. So you're probably familiar with the blue blocking literature. We talked a little bit about it earlier in the course. Some of the blue blocking lenses work, but most of the ones which you can see through and can't really tell that it's blue blocking, those don't work very well. But really, in your time of studying for exams, you should focus on reading written material before you go to bed. If you're going to study anything, really you should take some time to just relax and wind down. But I know that's kind of hard sometimes. So focus on written material and not screen time. There are a number of studies that have shown that during the day you accumulate memories in your short-term hippocampus, And then at night, during slow wavelength, non-REM, delta waves, there are these little spindles that come before it, and they show that there's really a lot of activity going on while you're sleeping, and particularly in the first half of the night, you mostly you have most of your deep sleep. Now, deep sleep is important because during that period of time, the literature would suggest that your hippocampus dumps memories into your cortex and into the outer parts, and you basically find storage spots for the things you've learned today. And then later in the night, you start dreaming more and REM sleep. And REM's kind of an interesting thing because, you've seen it's REM, rapid eye movement. It looks like lots of things are happening. That's mostly when you're dreaming. You actually dream during non-REM too, but the really bizarre dreams happen during REM sleep. And during that time, the dreams seem to be just kind of a side effect of what's going on. Your brain is going around, just firing things, looking around, and it's the time when you are making new creations. You have a problem, and people say to sleep on it. Well, when you sleep on it, what you're doing is you're letting your brain do the work and go around and making all these associations. Now, all of this is something that you want to have happen. You want to be awake during the day. You want to transfer memories from what you've studied during the day into long-term memory. And you want to get those creative associations working during the night. There's a number of studies showing that, for example, people who have had their non-REM, their slow wave blocked, they are impaired. There was a clever experiment done by a guy named Walker where people were wired up for sleeping, and then when he noticed that they were going into this deep delta wave sleep, they would nudge them a little bit, not enough to wake them up, but enough to break that deep sleep. Those people had a great deal of difficulty the next day remembering what they had learned the previous day in a task that was given to them, and they also had a harder time learning the task tomorrow, the next day. The point being is that if your deep sleep is disrupted, you're wasting your time studying during the day. You'll get a little bit, of course, but you will not be as efficient as if you get a good amount of sleep. And that amount of sleep should be 7 to 8 hours. There is no such thing as a sleep camel who can stay awake all week and then make it up over the weekends. You lose sleep, it's lost. What I'd like to do today is just give you an example. Again, we're going to go over an example literature article and one more time just kind of review how we calculate effect size. And if you're already really familiar with this, you can stop listening to the video now. If you would like to see one more way of the way I'll be thinking about it for the final, then you can go ahead and listen. So let's take this article, and this is kind of an interesting article. It was done by a guy named Viola and et al. And they were working. This paper is about workplace where the company had 2 floors of workers and they changed the lights, tested different lighting situations. They had an original set and then 2 new configurations. And they were wondering about the specifications that should be used in the workplace. They had 104 workers. They actually ended up with 94. And the 2 floors were very similar in terms of workers. And to get around the problem of any differences that did exist, they did a crossover study. So for 1 week, they took background or baseline measures using the existing lighting. And then after a week, over the weekend, they switched the light to either a blue enriched white light with 17,000 K, which was a very cool light and a lot of blue, and the other was just a white light that was 4,000 K. The order was balanced between the floors, meaning that it was the same number of workers, and they did the blue light for 4 weeks, and that group did the white light. Then they switched, and the white light people did the blue light, and the blue light people did the white light. Then they gave questionnaires and rating scales to assess their alertness, mood, sleep quality, performance, mental effort, headache, eye strain, and mood throughout the 8-week intervention. And they have peed all over this paper. They don't directly give you comparisons of means and standard deviations, except they were kind enough to give us a table. And actually the statistics they used were pretty good. Their implementation of it, not so much. But they concluded that the exposure to blue enriched white light during the daytime improved subjective alertness, performance, and fatigue. Let's kind of look through the figures and see if they have something that supports that. The questionnaires were the Pittsburgh Sleep Quality Index. These are all Likert type scales. Now let's look at the lighting. Here's the first figure. This was the blue light. So this is the spectrum. It goes from like down under, I don't know what the spectrum is, maybe it's down here. Yeah, from 400 to 700. And you can see there's this enormous peak in what would be about the 440 range, but there's also a pretty good density of blue light right here. And then the green and red are pretty similar in the two conditions. The difference is there's more density of blue here with a spike that's maybe a little thicker, but not that much really. This the white light one, in order to make the light white, they had to put in some blue there. So the baseline lighting, and notice that they did a nice job in the sense that all the y-axes are the same. So they're directly comparable. And the blue light is down lower. There's practically none except for this one spike. And then there's a little bit of green and a little bit of red. So this is what they started with. It wasn't very bright in that office, you can see, and they definitely increased the brightness regardless of which treatment condition there was. But this one increased it. Actually, it turned out, I think I have it marked in here, that the luminance, the brightness, was actually brighter in the white light condition, although 310 and 420 lux is not really super bright, but it's brighter. This was even less than that. So so that's those figures. That's what they're testing. And I liked that they used the baseline values for a covariate, but then they kind of didn't really use it so much. Like this is a change score figure. It's not an analysis of covariance, but this kind of makes the point. So this is the mean change from baseline, and the white bars are the white light, and the black bars are the blue light. And for alertness changed from baseline in a positive direction. For blue light, not much change at all, a little less. For the white light, same way with performance, went up a little. Evening fatigue, there was basically no change with white light, but and this they measured with a scale, and they noticed that people said they were less tired at night. They took the measure during the day, but they reported back remembering the night before. And this general sleep quality index showed the lower score is better, and both groups improved a little bit. The blue light improved more. And all through here you can see they're just giving this description in the results, wanting you to use the p-value as the indicator of significance. Just a reminder, we have learned that the function of the p-value is to rule out chance. It says nothing about the magnitude of effect. Sample size can make a really tiny p-value, or it can make a big p-value when there's a difference, a bigger p-value when there's a difference. Don't be fooled by a little p-value saying things are really, really significant. Now, table 1 here, this gives means and standard errors for the baseline, blue enriched white light, and so forth for these qualities. We find here that there's difference in the PSQI, and these are changes from I believe this is probably an overall F-test. It just says there's a difference somewhere in here. Here's another one where in this one they use the baseline as a covariate. Now, just from a statistical thing that's kind of interesting. They this is the main effect, but they also had an interaction with order. In a crossover design, that's a bad thing. You need to look at it, because what that means is that the effect of blue light depended on whether it was presented first or second in this study. And in fact, they did not explore that very well. They kind of did in graphs, but it's pretty confusing. They could have done a better job in talking about this interaction. But with the headache and eye strain, we can see all of these measures over here are significant except for the headache. Didn't seem to matter which group you were in. But also sleepiness, mental effort, your mood. Well, positive mood was affected, not so much the negative. Positive mood was higher in the blue light than in the white. Negative mood was about the same. All right, here's the graph that kind of shows the it's supposedly showing the interaction, but it's pretty hard to follow. Okay, now I have put together a little Excel spreadsheet to kind of remind us some principles on calculating effect size. Notice we're just doing the effect size here of difference between means. Remember that correlation greater than 0.1 is kind of 0.1's a minimal. It's really not very big at all. And if you're looking at the correlation for two tests that are supposed to be the same, you want those differences, that correlation to be up above 90. Also, the relative risk. Generally speaking, when you're talking about big trials with many subjects, you cannot at all rely on significance as an indicator of effect size. You want to find effects that are greater than 2. Those aren't very often you find those, but that's when you know you've found a difference. Other than that, an effect size that is or a relative risk that's greater than 2 is pretty good. 1.5 is probably the minimum. 1.6 maybe is the minimum requirement for that. All right, let's look and remind ourselves about this. So let's look at the sleepiness scale. And remember that in sleepiness, we were P equals 0.004 for the main effective light. And when we look at that, that's a score on a scale from 1 to 9, a score of 3.6. 9 is you're really sleepy. Well, hopefully if you're in work, you're not really sleepy. So those upper numbers probably aren't all that useful. And the standard error, remember the standard error is this hypothetical construct that if you had an infinite number of samples, you'd have a distribution of means. And the standard error is the standard deviation of the means of that hypothetical distribution. And for effect size, we need to convert that to standard deviation. So we have the mean at 3.6, white lights, standard error. The effect is, the P is 0.004, and the standard deviation is the average. Okay, so in order to get the standard error, you multiply the standard error times the square root of n, 94. There are 94 subjects that made it to the end. It's a crossover. You use all of them in this. So it's 0.13 times the square root of 94, 0.12 times the square root of 94, and you take the average of those two, and you get a standard deviation of 1.21. And then the effect size is the mean of the blue light minus the mean of the white light divided by the standard deviation, which is minus 0.36. Remember that our criteria for clinical relevance, where you can notice this effect of sleepiness, is 0.5, and this, or minus 0.5. In this case, it's minus 0.36, which is smaller than that. So it's a moderate to, it's a small to medium effect size. Good for scientific research, but not so meaningful for clinical effects. But not too bad. All right, so if we come down here, we notice, if we look down here, that these last three, difficulty focusing, concentrating, and blurred vision, which are things you don't really want to have on the job, those all did better with the blue light. The PSQI, the Pittsburgh Sleep Quality, that was a P of 0.02, and you can see that with that probability it's significant because it's less than 0.05, but the effect size is just 0.25. Now, in our work with effect sizes, we say that differences under 0.2 are trivial. And differences between 0.2 and 0.5 are kind of good for scientific sorts of things. They say there's something happening there, and maybe if you multiplied it a lot over a long period of time, that it's even possible that you might notice something going on there. But for the most part, there's not a big effect of that. So, when I would say their conclusion was that the blue lighting helped, and I think that is a fair assessment. It didn't make a huge bit of difference, but it did make some, and particularly in focusing and concentrating. So think about what you are now, at this time of this recording, you are locked into your house. You're not supposed to go outside, and all your studying and all your classes at this time are online. And so you have much more control over the lighting in your environment than you do when you're in the classroom. The classroom is for first, second, and third years, it's kind of blue poor, although I think they have been upgrading it a little bit to make it a little bit more blue during the day. You can solve this problem by getting a desk lamp or something through Amazon, or a light bulb through Amazon, that increases the luminance or illuminance, makes your environment brighter when you're studying during the day. You want that because that will help you concentrate. It will keep you awake. And so that's a good thing. Now, what you don't want to do is be in that environment at 8, 9, 10, or later at night, because that's going to keep you awake. And if you delay the time you have with if you have that bright light, it will delay the onset of non-REM deep sleep, which will defeat your purpose of studying, because your memories will not get distributed out into your long-term memory as well. And because you're delaying that action, you're cutting your night short, you're cutting off the opportunity for REM and dream sleep. So you want to turn off the lights, an hour or two before you go to bed, you want to sleep for 8 hours, and then you want to get up into a bright environment. And so open the windows. It's not real bright right now outside, but any sunshine is good when you can get it. So that's it.